Hi, welcome back to this class, Thermodynamics. In our previous discussion, we talked about ideal gas law, and we also talk about molecular properties of matter. In this video, we'll be continuing our discussion on the thermal properties of matter, but specifically we will be talking about molecular kinetic energy, which form part of the kinetic molecular theory of ideal gases. Again, with me in this course is Dr. Jonathan P. Manigo. The kinetic theory has been used in the formulation of ideal gas laws. We have this charge law, which states that at constant pressure, the volume of a gas increases or decreases by the same factor as its temperature. Mathematically, that is expressed as the ratio between the initial volume and temperature is just equal to the ratio of the volume and temperature at any given change of either of these parameters. And we also have this Boyle's law, which states that at constant temperature, the absolute pressure and volume of a given mass of confined gas are inversely proportional. That is mathematically expressed as the product of the initial pressure and volume of that gas would just be equal to the product of its pressure and volume at any given change of either one of these parameters. Talking about more on the kinetic molecular theory, there are basic assumptions. These are the most basic assumptions. First is that the volume occupied by the individual particles of gas is negligible compared to the volume of the gas itself. Second assumption is that the particles of an ideal gas exerts no force, attractive or repulsive force on each other or its surroundings. The third assumption would be gas particles are in constant randomized motion and move in a straight line until they collide with another body or particle within the enclosed container. Next assumption is that the collisions exhibited by gas particles are completely elastic. I hope you can still remember the difference between elastic and inelastic collisions. When two molecules collide, the total kinetic energy is conserved. That is, the kinetic energy prior to collision and the kinetic energy after the collision would just be the same. And lastly, the kinetic energy of the gas molecules is directly proportional to the absolute temperature only. No other parameters or other factors. This implies that all molecular motion ceases or vanishes if the temperature is reduced to absolute zero. That is at negative 273.15 Kelvin. So, speaking about kinetic molecular model, this is a model developed to visualize and to give interpretations with the basis of those assumptions. This model represents the ideal gas as a large number of molecules, a collection of molecules bouncing around in an idealized closed container. Assuming we have this two-dimensional container of these gas particles, and this is an idealized container. So based on that assumptions, these particles are moving randomly in all possible directions inside the container, and as they move, when they hit or bounce the wall or hit another particle, the kinetic energy is conserved. So because of this concept, because of this principle of complete elastic collision, again, the kinetic energy, the total kinetic energy of the particles involved would be the same before and after the collision. That means the speed of the particles prior to colliding with another particle or with the wall will be just the same after the collision. Remember, the kinetic energy is expressed as 1/2 mv square. If we will retain the kinetic energy to be constant before and after collision, then it would be safe to say that the velocities or the magnitude of the velocities before and after collision would just be the same. So looking into this illustration, if for this two-dimensional animation, we know that if we have a particle moving in this direction, that would be the direction of its velocity, where this velocity has components along x-axis, and that's initial, and it also has a component along the vertical axis. Here we have the vy component, and the direction of the initial velocity after collision would of course be changed. And in this illustration, in this particular example, the direction of the motion of the object or the particle is downward, slanted downward. Then of course we know that the velocity component along vertical axis would just be the same, that is downward. However, the direction of the velocity along x-axis would change as it bounces up from the wall after the collision. Now, again, under the assumptions of this kinetic molecular theory, the velocity would be, the speed would be the same. It's just that the direction of the velocity of the speed might change after collision. So the velocity component, for example, for this illustration, for this particular particle under consideration, the velocity component parallel to the wall does not change. However, the velocity component perpendicular to the wall, or we have this velocity along x-axis, then it changes after bouncing up from the wall. But then again, the speed or the magnitude of the velocity will still be the same. Speaking of collisions, this particular behavior of the idealized gas model give rise to some other properties of the gas, such as pressure and temperature. The pressure exerted as these particles hits the wall of the idealized container, the pressure exerted by these gases or this gas depends on the number of individual molecules or particles inside a specific particular volume. The mass of these particular particles or molecules, and of course on the speed of these molecules or particles. Taking from the concept of energy, we know that, for example, for the kinetic energy, we know that if we will assume a constant amount of mass, the only factor that could change the amount of the kinetic energy is the velocity of the particles. Therefore, for example, for this particular ensemble of particles moving inside the cylindrical container, if we are to sum, if we are to average the velocities of these particles, we should be able to identify that as the motion or the average velocity of these particles will have a greater value, then it would give us the idea that the kinetic energy, the total kinetic energy of the system is of great value also. And if the average velocity of these particles is just a small value, then of course the total kinetic energy would be of small value also. So from this, we know that pressure is just the amount of force exerted into a specific surface under consideration. We could have the relationship that the pressure inside the container would just be dependent on the mass of the particles involved, the velocity of the particles involved, and of course the volume of the container where the where these particles are moving. If we have higher velocities, we will have higher pressure. If we will have a small volume, of course, of considering the same number of particles and the same speed or velocity, then of course the pressure would be higher. And the more there are individual particles or molecules inside the container, then of course the pressure would also be higher. So we have this relationship that the pressure is directly proportional to the number of particles involved, the mass of these particles, and of course the velocities of these particles. And as we increase the volume, then the pressure would be lower, and as we compress the volume, the pressure would increase or would increase or will have a higher value. Looking back to the concept of translational kinetic energy, of which here we assume that the particles are moving in a straight line and changes its direction the moment it hits another body or it hits the wall of the container, then again, the kinetic energy of the gas molecules in the container is assumed to be dependent only on the mass, the number of particles, the volume of the space, and the velocity of this motion. And since this motion is highly randomized, statistically, it is customary to assume that instead of dealing with individual velocities, we have to average the velocities of these particles. I will not be discussing thoroughly how this is calculated statistically, but the velocities for this randomized motion of considerable many number of particles, we have this what we call the root mean square velocity, expressed as the root mean square. This is the most statistically practical approach in solving the kinetic energy of the system of particles of this randomized motion. So we have this velocity expressed as the root mean square VRMS is just equal to the square root of free RT over the molecular mass, where R is the gas constant. Plugging in this value to the kinetic energy expression, we have the Ke is equal to 1/2 mv square. Then we get this expression. We have the K, the kinetic energy translational, to be just equal to the 3/2 nRT, where again this nRT is taken from here, where we have this n is equal to m over m. So this is now what we call the average translational kinetic energy of the n moles or number of molecules of ideal gas. And we have this expression as the average translational kinetic energy of a single molecule. This is the molecular kinetic energy. With these assumptions and with these formulations, it is now clear to us that the average kinetic energy of gas in the air or the atmosphere is higher during summer season compared to winter season. Here in the Philippines, maybe we will not feel so much about this because we do not have a winter season, but it is obvious that for rainy season, it is the average kinetic energy of the air is lower compared to the average kinetic energy of our air during summer season. To help you visualize, I will now bring you to the PhET simulation. So here, we have oxygen. We have chosen the oxygen molecules at absolute zero temperature, or that is 0 Kelvin or negative 273 degrees Celsius. Based on our assumption, there should be no motion involved. However, if we will try to introduce some heat into the system, the particles, our oxygen molecules will now start to move, and our temperature rises from negative 273 to negative 271. As we raise this higher, as we introduce more heat, you see the temperature will also change its value. The temperature inside the container should increase, and since these particles has acquired some amount of heat, this will now be utilized in a form of kinetic energy. And because of that kinetic energy, we should be able to see motion of these particles randomly. See what will happen to these oxygen molecules at the highest possible temperature that can be given into the system. As you can see, the gas molecules here do not just exhibit translational motions. They also exhibit rotational motions. But in our assumptions, we did not include the rotational motions of these molecules. We only consider the translational motion of the particles. Now we are at around 1000 Kelvin. And it became obvious that the motion of these particles has become more random. Some are spinning faster, some are translating faster. Let's solve some examples. Here we have a 10-liter tank contains an ideal gas at pressure of 2 atm. What is the average translational kinetic energy of the gas? What is the temperature of this gas if there is a mole of gas inside? So we have pressure of 2 atm, and from our ideal gas law, we have PV is equal to nRT. And from our average translational kinetic energy theory, we have 3/2 nRT or 3/2 PV. Then just plugging in values, we have this average translational kinetic energy of 3039 joules. And from our kinetic energy theory, we have 3/2 nRT. Then we have this expression for T. Then we can solve for the temperature of the gas. That is negative 29.48 degree Celsius. Alternatively, we can also solve for the temperature using this formula, and the result would just be the same. So that's it for now. See you on our next discussion.